I am Mance Harmon here with Leemon Baird. Welcome to the next episode of First Principles. Leemon, today we're going to be talking about a topic that everyone has heard of, but very few people really understand. So, quantum computers.
Yes. Quantum computers are cool.
Quantum computers are cool. Okay.
They are.
So let's start with the very basics. What is a quantum computer versus a classical computer?
In a computer, a traditional classical computer, you have ones and zeros. In a quantum computer, you can have a qubit instead of a bit. And a qubit, a quantum bit, can be a 1 and a 0, or it can be both at the same time. And you can say, well, it's 3/4 1 and 1/4 0. Or you can even use amplitudes that have complex numbers in them. So you can have both 1 and 0 at the same time. Superposition of the two. What's more interesting is that if I had 3 bits in a normal computer, it could hold, 3 bits, 1, 1, 0, say. But in a quantum computer, if they're entangled, so they're connected to each other in some quantum sense, then you can have all 8 possibilities superimposed. It is 0, 0, 0. And it is 001, and it is 010, and it is 011, and 100, and 101, and 110, and 111. All 8.
At once.
At once. So it's in a superposition of all 8 of these at once.
And why is that a good thing?
Well, you could imagine I will do operations and have all 8 of them doing calculations at the same time in parallel, which would be great. Sadly, you can't do that. But you can take advantage of quantum mechanics to sometimes get a little bit of that kind of parallelism that is then much faster than a traditional computer. So you do all 8 things at once in some sense.
So you used a term.
Yes.
It was entanglement.
Yes.
Can you go a little bit deeper on what that is and what it means?
So it is not helpful if I have a bit that's a 1 and a 0, and another bit that's a 1 and a 0, and another bit that's a 1 and a 0. What I really need is a group of 3 bits that are a 000 and a 001 and a 010 and a 011, all 8 at the same time. When we connect them like that, it's called entangled. And so in quantum mechanics, when you're in 2 places at once, you're in a superposition of the 2 states. And if all these different things combine in the way I just described, we say they're entangled with each other. And the problem is, it can all fall apart. And it's really, really fragile. So it can decohere where they all fall apart, they stop being entangled, they stop being in a superposition, and this is now a 1, this is now a 0.
Okay. All right. So all of that is pretty abstract and pretty...
Yes.
Probably difficult for people to understand. Mm-hmm. Let's level it up a bit. Can you create normal, what we would call in computer science, gates?
Okay. So a quantum computer is made from these bits. During the time that they're in this weird superposition, you can do things to them, and they will change. So like I said, I could be in the superposition of all 8 states at once, and the amount that I'm in each state could actually change, and even its phase, which is this weird thing. So you could have them changing over time, and then at the very end, we have all 8 of them, each of them has an amplitude, then we make a measurement. When we make the measurement, we just get one of them. And its probability is determined by those 8 amplitudes. So you start with in all 8 states, you do operations that make them change, and all 8 of those amplitudes change. It's like I have a list of 8 numbers that I'm changing in parallel. There's the real power, if we can just take advantage of it. And then at the very end, I make a measurement, and then I only see one of the states. But the probability came from that. And I told you make operations along the way. In quantum computers, they call those gates. In a regular computer, on a computer chip, the circuits are just lines of atoms that electrons can flow down. That's what a circuit is, or, a wire is. Mm-hmm. And then a gate is a way that you have 2 inputs come in and an output goes out, and you can control it. And
like an AND gate or an OR gate.
Right. So a gate is a thing. It's a piece of silicon that's been doped and is a shape and so on. Mm-hmm. In a quantum computer, a gate is not a thing. It's something you do to it. It's not an object, not a physical object. It's something you do to the computer. So I have my 3 quantum computer qubits sitting here. They're entangled. They're in a superposition. They're really representing 8 different numbers. And then I do something to them. I hit them with radio waves, or I shoot a laser at them, or I use electricity to move them, or whatever. And then the result is all 8 of those numbers change. that thing I did to them, we visualize as if it were a gate in a circuit, and we call it a gate. So a gate is not a physical thing. It's something you do to your bits, your qubits, to change their state. And I said that with 3 qubits, I have 8 numbers. And I'm changing all of them. I hit it with radio waves, and all 8 of them change. Well, with 10 of them, it's like 1,000 numbers. With 20 of them, it's like 1,000,000 numbers. With 30 of them, it's like 1,000,000,000 numbers. So there's the huge power of quantum computing. With a little operation on 30 qubits, I'm actually changing 1,000,000,000 different numbers. The problem is I can't actually see those numbers. And when I do a measurement, I just see one state. And those numbers just affected the probability that I would see that particular state. So we have to somehow get it to ask it a question where the probabilities are all the same of all the gazillions of possibilities, exponentially many, but then we have to do a sequence of gates that will cause it so that one of them has a high probability and all the rest have low, and then we have the right answer.
Okay. So is it the case then, based on this conversation,
Yes,
that the real value proposition of quantum computers is the ability to process information in parallel, degrees of parallelism that we haven't been able to process before?
we should not think of it that way. Because if you think of it that way, you're going to think it's much more powerful than it really is.
Okay.
It is allowing us to, in a sense, have this exponential amount of information floating out there in a way we can't see, and then, in a sense, operating all of it in parallel. But we can't do arbitrary operations, and so we're very, very limited in what we can do. We only know a tiny handful of things we can do on it, but we can do those things if we ever build one, which we also don't have big enough computers to make them useful. But if we have someday really big quantum computers, there's a tiny list of things that we know how to do, and they will be exponentially faster than traditional computers.
Okay, fair enough. So these are not going to be general purpose computers.
No. They could run an ordinary program, but it'd just be a super slow way of doing it.
Right.
And even an ordinary parallel program, better to run it on your GPU. They are only for these very specific operations. They'll be like a coprocessor that just solves one little tiny problem, and your ordinary computer will talk to it and give it problems to solve. That's what it is.
Okay. So that just begs the question, right? What problems is this going to solve?
Yes. So the big thing that Shor invented was a way to factor big numbers.
Shor is
a person who invented a way to factor big numbers.
Okay.
Okay, that's his last name is
Yes,
Shor.
got
Yes,
it.
okay. Shor's algorithm. And so if I tell you 3 and I tell you 5, you know how to multiply them and get 15. If I tell you 15, it's a little bit harder to figure out the 3 and the 5. When I was teaching some young people, that was a hard problem. In factoring, you have to think of all the different possibilities. If you have really big numbers, everybody knows how to multiply them easily. We don't know how to pull them apart and factor them again. With a quantum computer, the best algorithm we know for quantum computers and the best algorithm we know for classical computers, quantum computers are exponentially faster. And it turns out that lets you break all of the commonly used asymmetric cryptography in the world right now. That's a useful thing.
Right.
Okay.
That's a problem.
That's a problem.
Yeah.
But that's something that can be used for and has a huge power. What else could you use them for? Now, if you're doing just brute search in a very stupid way, it can make you square root faster. I don't know if that matters. So if you ever heard of the traveling salesman problem, okay, really hard problem. You have a bunch of cities, you have to go through all of them and come back to where you started. You want it to be as short as possible. To find the absolute perfect solution is incredibly hard. We can only have our computers solve it for a small number of cities. A quantum computer with Grover's algorithm could do twice as many cities. That's it. I'm not sure that helps.
Right.
And that's if you're doing a brute force, try all the possibilities. If you're doing something very clever, like using AI, then we might give you an answer that's maybe not perfect, but really good, really fast, and it's really good. And quantum computers don't help at all as far as we know. So it doesn't really help all that much.
Yeah. So when solving that category of problem, the notion is that other techniques perhaps are going to be as good, maybe even better than quantum computers.
Probably. So for right now, if you have an NP-complete problem like traveling salesman, you're probably better off with traditional computers. There's no particular reason to think that quantum computers are going to give us any advantage. You're probably better off with deep neural networks, which are very memory intensive and therefore probably not ideal for quantum computers. And then we don't even know of any way that quantum computers would help with them at the moment. There are some things we can do in AI with quantum computers, but we don't know that they're actually of any use whatsoever. So probably for these sorts of optimization problems, you're better off just with traditional computers. But for factoring, you're better off with a big quantum computer. Much, much faster. The sun will burn out before my computer can do it, but a quantum computer can do it in minutes.
And the most obvious application of factoring is
Cryptography.
cryptography.
In fact, I'm not actually aware of any other practical uses of factoring giant composite numbers. It is only cryptography.
Right.
And if you're familiar with RSA that used that, it breaks it. If you're familiar with elliptic curve, yeah, it breaks that too. Okay. But we have other solutions.
Okay.
So quantum computers can do that. They can also simulate quantum systems. Oddly enough, if I have a bunch of atoms doing quantum type things, a quantum computer can be good at simulating that atom.
Okay,
That collection
so that's
of atoms, that
interesting.
molecule.
Does that help in terms of research, theoretical or otherwise?
Maybe. I don't know. So maybe you could use it for protein folding, understanding how protein's going to fold up. On the other hand, AI systems like AlphaFold is an AI system that can predict the folding and does a really good job. But it's just guessing. This thing would be actually simulating. Maybe the simulation is better. It could do a better job. And maybe that's helpful in medicine and helpful in chemical research and trying to make better batteries and those sorts of things. It's not obvious that it would be a huge leap forward in those things. If you want to build a new medicine, you can think of a sequence of DNA and then try to figure out what molecule it would create. Okay, you could do that. But then what will that molecule do? Well, the shape matters, so the folding matters. But then what does it really do when you give it to a person? Well, that matters. You have to simulate the entire body. And that's way beyond anything we're ever going to be able to do on a quantum computer. So you can simulate some things in it, but for bigger questions, like what does this drug actually do to a human, you're going to have to use more traditional techniques. But it will be helpful. And so, this may be another tool in our tool chest to help us in medicine and in chemistry and in battery research and these things.
So what is the motivation behind pursuing this line of research? Is it pure computer science, or are there, I could imagine certain agencies or, actors that want to crack crypto. Is that it?
That's pretty much it. The real interest has been in cracking crypto, and the real interest is in, well, if my enemies can crack the crypto, I want to know about it, so I'm going to do research also.
All right.
Okay. Then there is some of this other stuff. You could do Grover search, which is the square root speed up. That's slightly useful. You could do this quantum simulations, and there's other quantum simulations that physicists are just interested in simulating. So they would love to get their hands on this for quantum simulations. And maybe someday we'll discover other things that are really, really useful. We just haven't yet.
Right.
But maybe we will. Whether they're better than AI, I don't know, but we'll see. But that's the main impetus has been the cryptography issue. It's a real threat to cryptography, and people are saying, well, if anyone's going to invent it, I want to invent it so my enemies don't get it first.
Right.
Right.
Okay. So, obviously you and I, as
Yes.
the founders of Hedera, have an interest in ensuring that Hedera
Yes.
is secure. So Hedera uses cryptography, obviously.
Yes.
Is Hedera secure against quantum computers?
All right, so we're in really good shape. So here's where we are in Hedera. We use 4 cryptographic primitives. We use hashes in the hash map. So we have the hash graph that has hashes in it, and we have the history of everything that's ever happened that's tied together with hashes, sort of like a blockchain. So we have hashes all through the system. And we use SHA-384, not 256. Why do we use the extra bits? It's so that we're CNSA compliant, which is, the government requires that for top secret information. And why does it require it? Because it is, we believe, secure against giant quantum computers. So the belief is, even if you took, all the atoms on Earth and turned them into giant quantum computers, you would not be able to break SHA-384. SHA-384 is thought to be secure against quantum computers forever. That's pretty good news. And we use SHA-384. Most blockchains use SHA-256. Theoretically, quantum computers could break it, so they'll someday have to go to 384. Although, to be honest, I think 256 is secure enough. To use 384, you have to have a lot of qubits, and I think it's going to be hard. Oh, I said qubits. I never talked about logical qubits. So qubits are really bad. They make errors. And so what you can do is take a whole bunch of them and apply error correction to simulate one shiny qubit that doesn't have any errors. And so I take a whole bunch of my real qubits and they simulate one good qubit, error-corrected qubit, a logical qubit. And I take another big bunch of them and they simulate my second logical qubit. And I just keep going with all these logical qubits. And so in order to build truly big, useful quantum computers that are a threat to cryptography, you're going to have error correction. So you're going to have a circuit with low enough error to begin with, and then lots of extra qubits that we can combine into groups to make these pretend logical qubits. Okay. So
Hedera has hashes.
Hedera has hashes, and our hashes are secure. 384, SHA-384.
Yep.
Really secure. We also do, we have symmetric encryption that we can do, which is AES. We use that over the wires. And AES 256 is believed to also be post-quantum. People say, oh no, quantum computers can break all cryptography. No, the most common crypto system is AES, and it can't break that. And no one thinks it'll ever be able to break it. This is, you can always discover new math tomorrow. But right now, the whole world thinks that AES 256 is totally secure against quantum computers. This is the current understanding. And it's been around a long time, and people looked at it a lot. So we don't use that for very much, but you could use that. We do TLS connections between our computers. So the information sent between them is encrypted. Honestly, the whole system would be secure even if we didn't do that. But it just kind of makes sense to encrypt things when you can. And so we use AES to encrypt. Yeah. But we have to do a key agreement at the beginning when we first start the connection. And that is TLS. It uses things that quantum computers can break. So someday, people will have post-quantum TLS that is secure against quantum computers. And we know how to do it. It's not all that inconvenient. There's lots of demos that have been done. And at some point, it will come out as a standard. And we'll switch to that for our TLS connections, which don't really matter anyway.
No.
It's not like we're encrypting information that has to stay secret for decades. And that 10 years from now, somebody might, today they might record it. And then 10 years from now, break it. That's what a lot of people are worried about with their secrets. We don't have any secrets, so it doesn't matter. So that's a good deal for us. Which brings us to the fourth thing, which is digital signatures. Digital signatures are critical throughout our system. When you sign a transaction, you have to digitally sign it. And if people could forge your signature, they could steal everything from you. Internally, we do signatures on consensus. And if you could forge these, you could screw up our consensus. Signatures are important everywhere. And we use secure signatures, again, CNSA compliant for our internal signatures, 3000-bit RSA and other things that are CNSA compliant. But they are not post-quantum. And maybe in a decade or two, we will have computers that can actually break these signatures. So we're going to have to switch to post-quantum signatures. Oh, by the way, maybe never. It is conceivable still that we will never have big quantum computers that can break actual real-world cryptography that are big enough to do it. But we could have it in a decade, or two, or less, who knows. So that is something we have to do. So we have designed our entire system to make it easy to plug in a new crypto system. And we can plug in a new signature system easily. And we will do that when Falcon is standardized. So NIST had a contest to find the new crypto systems that are secure against quantum computers, post-quantum computing. And the signature system, Falcon, is the one that I want.
I don't want that you want.
Yeah, I don't want dilithium. It's bigger. It has bigger signatures. I want Falcon with
When are the
smaller
results
signatures.
of this competition?
Those are the two signatures.
Okay.
And then there was Kyber was for encryption. And then Sphinx actually got it approved too, which is good. Sphinx is guaranteed to be secure. I'd be shocked if Sphinx isn't secure. But it's something like 45 kilobytes for a signature, so maybe not all that great. But it's everybody knows Sphinx is secure. But the other three are probably secure. And Falcon is the one that I want, although it hasn't yet been made a standard. It just won the contest. And it has a little bit smaller signatures. So we will switch. When it becomes a standard, what we'll switch to is probably Falcon. And maybe we'll go to dilithium. I don't know. Probably Falcon. And when we go to Falcon, what we'll do is a hybrid system. So we'll say everything has to be signed by both Falcon and RSA, both. And unless both signatures are there, we don't believe it. And that way, if someday somebody discovers a flaw in Falcon, we're still secure because of RSA. They'd have to discover a flaw in Falcon and have a gigantic quantum computer to break us. Oh, and even better, there's no harm of them going back and breaking historical stored information. That's not a danger because there's no secrets. It's just digitally signing things. So they have to break it in real time. And so if we knew that something bad was going to happen next year, we could switch things today and we'd be fine. And this is true of all the blockchains. They're all going to have to switch this way. For some it's easy, for some it's hard. For us it's very easy. And we'll expose it to users and users can sign too. But, a kilobyte signature is inconvenient. And you have to pay a little bit more for more bytes.
So there were two questions. You just answered one of them. What we're talking about applies to the industry. We're talking about blockchain industry or DLT industry as a whole. It applies to everybody.
Sure.
And is it going to result in a performance hit?
Yes.
On everybody?
On everybody. I hate that. So, with the right hardware, you can make signing and verifying signatures fast. That's not a big deal. But they're bigger. Instead of 32 bytes, you have a kilobyte or 2 kilobytes or 45 kilobytes or something. Depends on which system you're using.
So
that's what I hate is the size of the signatures.
Right.
And the size of the public keys, which are also bad.
Yeah.
Yep. Classic Michaelis, I think, can do better on one but not the other. But it's bad. Mm-hmm. So the whole industry will have to switch eventually. And we are poised to switch as soon as there's an actual standard. We're going to wait for the standard. There's no rush. It's not going to happen tomorrow. But we will allow this as soon as we need it. And so the main effect of quantum computers is to force everybody to use something that quantum computers can't affect. It's kind of a pain. In my world, quantum computers are sort of a mostly negative thing. But if I wanted to do quantum simulations, then, they'd be a very positive thing. But,
okay.
In my world, it's just negative. But it's not that big of a deal. It's not the end of the world.
There's a lot of talk about it. I mean, we've heard about it for years and years.
Oh,
now.
Yeah. Huge progress recently, too. Lots of progress. IBM is a council member. They've done huge progress. And I think Google's working on it. Lots of people.
So how close is it? When do you think this is going to affect us in terms of needing to change out the crypto?
Quantum computers able to break our 3,000-bit RSA, it could happen in a decade. It could happen in the next 10 years. Or 20 years. Or never. I don't think it's happening this month. But it could be a decade. Who knows? And the standard from NIST will probably be next year. We'll probably implement this next year, which is way years ahead of time of what we need. But eventually it might happen. It is very possible. And the progress recently has been accelerating. Error correction has made huge progress on how many bits you need, qubits you need to make a single logical bit. And hardware has been improving bit by bit, so to speak. Slowly, hardware has been improving. So maybe we'll get there. I hope so.
But importantly, classical computers are going to be with us forever. Or at least they're not going to be displaced by quantum computers.
No. Quantum computers are like a coprocessor. They will never replace the classical computer because there's so few things they can do.
Yeah.
So your normal computer asks it to do this one little thing, and then you come back to your normal computer. Sort of how GPUs originally were just doing graphics, although now they do everything.
Yeah.
Yeah.
So, that's a good point. I mean, we may find other applications.
We may, but we've been looking for 20 years. But we may find other applications.
Okay, so that one was pretty deep, but a really interesting topic, one that has been discussed for years now, and hopefully we'll find some value in that. All right, thank you for joining us, and we look forward to seeing you next time.
Yep, we'll see you next time. Thanks.